Welcome to this explainer. Today we're diving headfirst into the hidden and honestly fascinating world of metal degradation. It's a world that operates totally silently all around us, eating away at bridges, pipelines, and yeah, even your car. But it's not magic, and it's certainly not random. By the end of our time together today, I promise you're going to see the structures around you in a completely different light. I mean, think about it for a second. Why do these incredibly strong, heavy, resilient metals just naturally crumble into flaky dust? We see rust literally everywhere, so it's super easy to dismiss it as just, an inevitable side effect of leaving metal out in the rain. But let's challenge that for a minute. What you're actually looking at when you see everyday decay is not some random chemical accident. It's a highly organized, completely invisible microscopic electrical circuit hard at work. So let's dive into exactly how this happens.
Here is our game plan for today. We'll start with 1, the hidden electrical circuit. 2, the 4 essential cell components. 3, oxidation and reduction reactions. 4, the rule of electroneutrality. And finally, number 5, the birth of rust.
All right, jumping right into section 1, the hidden electrical circuit. First things first, we kind of need to reframe how we look at corrosion. We have to stop viewing it as a mistake or an accident. As our source material perfectly puts it, corrosion by its simplest definition is the process of a metal returning to the material's thermodynamic state. You see, metals like iron, they don't just naturally exist as shiny, strong beams in the earth. We mine them out of the ground as oxides or sulfides, and then we use a massive amount of energy to refine them into useful engineering materials. But those refined metals, they are fundamentally unstable. They inherently want to return to their natural, lower-energy oxide or sulfide states, and they accomplish this return journey through electrochemical reactions. Basically, they're just following the laws of thermodynamics. Which brings us to section 2. The 4 essential cell components.
So now that we know why metals want to degrade, what does this whole electrochemical reaction actually need to run? Well, for a corrosion cell to function at all, it absolutely must have these 4 core building blocks. First, you need a metal anode. Second, a metal cathode. Third, an electrolyte. And fourth, a metallic conduction path connecting that anode and cathode. Now, if you're sitting there thinking, wait, that sounds exactly like a battery, you hit the nail on the head. A corroding piece of metal is literally just a short-circuited galvanic cell. The energy of the metal is being actively dissipated as electricity. And the craziest part? If you remove even one of these 4 components, the entire corrosion process just completely stops dead in its tracks.
Let's look a little closer at the 3rd component on that list, the electrolyte. An electrolyte is basically an electrically conductive solution that sits in contact with both the anode and the cathode. Now, what's really interesting here is that pure water is actually a pretty terrible conductor of electricity. But here's the catch. Environmental moisture is almost never pure, right? It's full of conductive salts, dissolved atmospheric gases, or acids. Just think of sea spray or acid rain. This contaminated moisture provides the perfect carrier. It essentially acts as a superhighway for charged ions to transport positive current straight between the anode and the cathode. All right, moving on to section 3. Oxidation and reduction reactions. So, we have our mixed-shift battery built. Now let's zoom right in on the specific chemical combat happening simultaneously at our 2 distinct electrode sites. The absolutely crucial point here is understanding the distinct roles these 2 areas play. Over at the anode, we have the oxidation reaction. This right here is where the actual destruction happens. The metal atoms lose their electrons and dissolve straight into the electrolyte as positively charged metal ions. But conversely, over at the cathode, we have the reduction reaction. The cathode itself doesn't actually dissolve. Instead, the electrons that were just released by the anode travel over to the cathode and get consumed there. In everyday water-based corrosion, those electrons are usually consumed by reacting with stuff in the electrolyte, like dissolved oxygen or hydrogen ions. Let's actually look at this dynamic in action. Take a look at this classic galvanic cell setup with an iron electrode and a copper electrode, sitting in an electrolyte. Because iron is a more active metal, it automatically acts as the anode. If you look at the iron side, you can literally see iron atoms losing 2 electrons and dissolving into the solution as Fe2+ ions. That's our oxidation. Now follow those dotted lines. Those negatively charged electrons flow through the external metallic path, the wire, right over to the copper cathode. And at the copper surface, the reduction reaction takes place as those incoming electrons are consumed by hydrogen ions in the solution, bubbling off as hydrogen gas. So the end result? The iron is totally destroyed while the copper remains completely protected. Next up is section 4, the rule of electroneutrality. Okay, so we've got electrons flowing, but there is a strict physical law acting almost like a traffic cop that governs the entire speed of this microscopic system. This brings us to the rule of electroneutrality. As our sources clearly state, the total rate of oxidation must equal the total rate of reduction. Think about it. A corroding piece of metal simply cannot accumulate a net electrical charge. You can't just have this massive pileup of electrons waiting around. Because the electrons freed up by the anodic oxidation are the exact same electrons being consumed by the cathodic reduction, these two tethered reactions absolutely have to proceed at the exact same time. And not only at the same time, but they must proceed at the exact same rate. This required mass and charge balance is absolutely vital to wrap our heads around. It essentially means that the rate at which the environment can consume electrons at the cathode perfectly dictates how fast your metal is dissolving over at the anode. This constant flow of electrons is known as the corrosion current. So, if you were to measure this current, you are directly measuring the rate of material degradation. Fast reduction means fast oxidation, which means incredibly rapid destruction of the metal.
And that brings us to our final section, number 5, the birth of rust.
Let's bring all these abstract rules we just talked about together using our ultimate relatable protagonist, iron. Notice the water droplet sitting right there on the steel surface in this diagram? This represents what we call a concentration cell. Guide your eyes to the very center of the drop right on the metal surface. Because there are lower oxygen levels right there at the center, this specific area becomes our anode. The iron here gives up its electrons and dissolves into the watery electrolyte as positively charged ferrous ions. Meanwhile, out at the periphery of the drop, where oxygen from the air is plentiful, the metal acts as the cathode. The electrons travel through the metal out to those edges, where they're quickly consumed by oxygen and water to form negatively charged hydroxide ions. So here is that exact sequential chemical transformation broken down step by step. Step 1, the anodic reaction. The iron oxidizes, losing electrons to become Fe2+ ions. Step 2, the cathodic reaction. Oxygen and water pick up those exact same electrons to form OH- ions. Step 3, these positive and negative ions migrate through the electrolyte towards each other and combine to form ferrous hydroxide. Finally, step 4, with even further access to oxygen, that ferrous hydroxide oxidizes and loses water to become hydrated ferric oxide. And that right there is the highly visible, flaky red material we all commonly know as rust.
Now, here is a wild, surprising detail that is absolutely crucial for understanding why rust is just so damaging. The rust doesn't actually form directly on the dissolving anodic spot. Because the positive iron ions and negative hydroxide ions have to migrate through the water to meet up, the insoluble rust precipitates out halfway between the anode and the cathode. So why does that matter? Well, because it forms completely away from the actual corroding surface, the rust doesn't block the anodic reaction site. It doesn't form a nice protective seal. Instead, equilibrium just forces the anode to keep supplying more and more ferrous ions, allowing the invisible destruction of the solid metal to rapidly continue right underneath.
Which leads us to a pretty thrilling conclusion. We've learned today that corrosion is really just an electrical circuit fueled by electron transfer. And we know that the anodic dissolution only happens when the metal loses its electrons. So the ultimate million-dollar question is, if this whole thing is just a circuit, couldn't we force an excess of electrons into the metal from an external power source to just stop this destruction entirely? Well, the answer is an absolute yes. Engineers use this exact science for a genius technique called cathodic protection. They literally pump direct current into pipelines and bridges to turn the entire structure into a protected cathode, basically halting the anode's decay right in its tracks. And honestly, that is the incredible power of truly understanding the electrochemical mechanism of corrosion. I really hope this explainer has sparked your curiosity to see the hidden electrical circuits operating all around us.